Okay, in this video we're going to make a model that can be used both to show conjugate and isolated double bonds along a carbon chain. What we're going to do is take the black 260 balloon, that's going to be our carbon backbone. We're going to take 8 5-inch clear balloons that represents the orbitals of the pi bond overlapping. We're using our Qualitex pump. We're going to take and put 5 pumps of air into this black balloon. 1, 2, 3, 4, 5. And give it a little burp and then tie it off. So that leaves about a 4.5 inch to 5 inch tail. That's uninflated. What we're going to do first is make a 1 inch bubble. This is the end of our carbon chain. It's going to continue on as we go from right to left. We're going to take the nozzle and we're going to twist that carefully into that joint. That creates a pinch twist. Since this is the end of the chain, for stability, we're going to do that again. We're going to take a 1 inch bubble, carefully pinch. So we have 2 pinch twists at the end of the chain. The next step for the carbon-carbon bond, about a 4 inch bubble, followed by a 1 inch bubble. And we're going to pinch twist that. So that's now carbons 1 and carbons 2. I'm going to make another 4 inch bubble, followed by a 1 inch bubble. And carefully pinch that. So that's now carbon 1, carbon 2, carbon 3. We're going to make 2 more carbons on this. Another 4 inch bubble, followed by a 1 inch bubble. Notice I'm staggering it on purpose, as a normal carbon backbone would be. 1, 2, 3, 4, and now the 5th carbon. And pinch that off. The rest of the balloon we could cut off, but for purposes in class it doesn't really matter. We can just say that's an R group hanging off here. We're looking at these 5 carbons now in particular. The next step is to attach the 5 inch balloons to show the p orbitals that are overlapping. We do that by taking the clear balloons. We put 3 pumps of air into each of those balloons. So there's 1. And here's 2. We tie those together. So that forms our orbital. We're now going to attach that at the end. And we twist those horizontally. You can see why we put 2 twists at the end, because that stabilizes those 2 balloons, locks them in place. We're going to make an isolated system first. So we're going to take 2 more balloons, 3 pumps of air in each. And the second one. And again, we'll tie those together. And put those at carbon position number 2. So now you can see the orbital-orbital interaction. That's a sigma bond. These represent the pi bond, the 2 orbitals that are overlapping and interacting. What we're going to do is make an isolated one, so at carbon 3, that's going to stay empty. We're going to then next, at carbon 4, put 2 more balloons. Makes 3. And 1 more. Okay. Let me tie these together. That goes at position 4. So that's now locked into place. Now obviously this is isolated bonds. You can see there's a gap between the 2 double bonds, which means that there's not going to be a continuous interaction across the system. So we're making the isolated case first. Again, our last set of balloons represents the other carbon and its p orbital. It's going to interact to form the pi system. So again, we tie that together and we put that in place at position 5. So now in class you can see this is one isolated double bond, a second isolated double bond. They're separated by a carbon in between. If we want to show a complete conjugated system, all we have to do is simply move this orbital into the center. And now students can see that the orbitals continuously overlap in a pi conjugate circuit. So in a conjugated system, we see this continuous orbital interaction. And you can easily transfer this back and forth to show isolated and conjugated. And that's all there is to it.